Alright, so this is example 1 in module 1, and in this video I just want to take the answer that we got in the previous video that it was done symbolically and plug in the values that were given for the different parameters to actually get a numerical value for this force. I do want to point out that there's an edit to the video that was posted that points out that this squared here was dropped in the final answer. So if you're watching the video around the 11 minutes 26 second mark, when I'm copying the denominator at the end of the video, I dropped this squared. So it really should be an R1 squared plus an R2 squared, and then that quantity is squared. Okay, so when we're plugging in physical quantities to do some sort of calculation, we have to pay attention to the units. And these are the quantities that were given in the problem, right? So we've got the initial charge of both spheres, the radiuses, or the radii of the spheres, and we have the distance between the centers. Now, we have to make sure that we get the units correct to write down our final answer in the correct units. So probably what I would say most students find the simplest method for making sure that the units are done correctly is to just convert everything that you're given into the base SI units. So for example, I have Q1 as 10 nanocoulombs. So we would convert that to coulombs before we tried to do any numerical calculations. Same thing with Q2. And then I have all of these lengths in centimeters. We would want to convert those to meters before we did any numerical calculations. And the reason that we would want to do that is because if I write down, so I have Coulomb's constant here, Coulomb's constant has a numerical value that is 8.99 times 10 to the 9, but that's assuming that we're in the base SI units, right? So if I try to do a numerical calculation with nanocoulombs, then this coulombs squared is not going to cancel with the nanocoulombs, right? So I can just plug in all the values that I'm given and do the calculation, but then I would need to make sure that I propagated the units correctly so that I could unit convert this to newtons in the end. So let's write down all of our quantities in the base SI units. 10 nanocoulombs is going to be 10 times 10 to the negative 9 coulombs. Negative 2 nanocoulombs will be negative 2 times 10 to the negative 9 coulombs. 2 centimeters is going to be 0.2 meters. 4 centimeters will be 0.4 meters. And then 10 centimeters will be 0.1 meters. Alright, so if I write all of these down in the base SI units, then I can just do the calculation and I won't have any problems with the units on K not canceling the units in the quantities that I have. Alright, so let me pre-calculate a couple of things that are going to be needed. So I'm going to need Q1 plus Q2 here. So I'm just going to go ahead and calculate that. That's going to be 8 nanocoulombs, which I'm going to write as 8 times 10 to the negative 9 coulombs. I'm going to calculate the sum R1 plus D plus R2. That's going to be 16 centimeters. I need R1 squared and R2 squared. Looks like I dropped it there again. So I'm going to calculate R1 squared and R2 squared in terms of meters squared. Right, that needs to be in meters squared, not centimeters squared. Alright, so I take all of those and I plug them into the equation that I wrote down for the force. So here's Coulomb's constant. Here is R1 squared. Here is R2 squared. And then this is Q1 plus Q2, and then that quantity is going to be squared. In the denominator, I have R1 squared plus R2 squared, and then that needs to be squared. And then this is R1 plus D plus R2, and then that is going to have to be squared. So notice that I wrote down all of the units here so that I can collect them all together and make sure that the final answer is going to be in newtons. If I do the unit analysis, or if I collect all the units and I don't get the units to cancel such that I'm left with newtons, then it means that I've probably made a mistake somewhere. That's actually a good way to check if you've got the correct answer, is to see if the units come out correctly. So if I just take all of these numerical values at the top, well, including this as well, and multiply those, I get 3.68 times 10 to the negative 13. And then if I do the same thing for the denominator, I get 1.024 times 10 to the negative 7. And now I'm going to collect all of the units. So here are the units that were on Coulomb's constant, here are the units that were on R1 squared, here are the units on R2 squared, and then here are the units on that charge squared. Here in the denominator, I've got a meters squared plus a meters squared. So that's going to give me meters squared. When I add two quantities with the same units, the result has the same unit as well. But that sum is being squared. So really, I'm going to get meters to the fourth there. And then I've got a meters squared here. So if I go through to check that my units all, or which units cancel, I would have the coulombs cancel. I have a meter squared in the numerator and a meter squared in the denominator. I have a meter squared in the numerator and a meters to the fourth in the denominator. So I'm left with newtons, which is good. That's what I expect the force to be in. All right, so this is the force in newtons. That's it's a small number if we express it as newtons. Times 10 to the negative 6 is micro. So I could write this as 3.596 micronewtons.